We are Unit 4, Day 33, 30, and 34 notes. This is Part 2. Um, this next problem, polynomial functions deal with critical numbers where the first derivative is equal to 0. Since that initial investigation of these properties, we've added on that there's a time when a function could possibly not be differentiable. So an example is when a function of a graph, the graph of the function, has a cusp. So, but it still doesn't exclude the existence of a relative max or min. So we're going to look at an example of that right now. So um, analytically find all intervals where the function is equal to x plus 2 all to the 2/3 plus 1 is increasing, decreasing, or has a relative max or min. Sketch the graph using a graphing calculator and on the grid to the right to verify our analytical results. Okay, so a lot going on there, similar to what we just did. So let's first write out the original function and take the derivative. Okay, so I've taken the derivative using the chain rule, and to simplify it, whenever I have a negative exponent, let's put that in the denominator, and I'm going to write these as two separate ones right now, two separate fractions, and that'll be x plus 2 to the positive 1/3 now, and I'll leave it to the positive 1/3, but we know that's the cube root, and let's write it as one fraction, so that's equal to 2 all over 3 times x plus 2 to the 1/3. And let me just make it look a little prettier by putting the 2 right in the middle. Okay? Now, I want to find out where this equals 0. And I'm not going to get a solution there. So, let me actually show you why it can't equal 0. So if I come over here and put all this stuff here, so x plus 2 to the 1/3 equals 0. Hey, how do I get rid of this fraction? I multiply both sides by that. So when I multiply the 0 by that, it goes to 0. So it's really saying where's 2 equals 0, and that never happens. So, but what I can find out is I can get a 0 in the denominator if x equals negative 2. Negative 2 plus 2 is 0. Cube root of 0 is 0. Times 3 is 0. And then it's going to be undefined. So the function is undefined when x equals negative 2. And again, let me erase that and actually show you how we did that. Again, when do I know any function is undefined? Hey, when the denominator is set equal to 0. So if I just set this equal to 0, how do I get rid of the 3? Divide both sides by 3. So that's gone. That's still 0. Hey, how do I get rid of the 1/3? I cube this side, cube this side. So cubing something to the 1/3 is just going to be x plus 2. That's the cube root of 0, which is just 0. Subtract 2 from each side. We get x equals 2. Okay? And it should be x equals negative 2. All right, now let's do a sign change chart. Okay, and we'll slide back up in a second here. So negative 2 is where it goes to 0, so I need to pick a value less than that. Let's just pick negative 5, and a value greater than negative 2, let's pick 0. And again, what was the derivative? It was 2 all over something. So we know the numerator is going to be positive. So when I substitute negative 5, the numerator is going to be positive 2, so that's positive. Negative 5 would be negative 5 plus 2. It's a negative number. Cube root of that is going to be negative times 3 is going to be negative. So I'm going to get positive divided by a negative, which is going to be a negative. 0, 0 plus 2 is positive 2. Cube root of positive number is going to be positive. Times 3 is positive. We already said the numerator is always going to be positive because it's just positive 2. So this function is decreasing, hitting a value of 0, excuse me, a value that's undefined, sorry, and then positive. So let's answer those questions. Same questions we just answered in the part 1 of the notes. Okay, so original function's increasing when the derivative is positive. We said it's positive on the interval from negative 2 to positive infinity. And the original function is decreasing when our derivative is negative. When's the derivative negative? From negative infinity to negative 2. Okay, now let's talk about relative min and relative max. Okay, we find out the original function has a relative min at x equals -2 because the derivative changes from negative to positive. Now this is the first example where it went from negative to positive but didn't go through 0. It jumped, it was undefined, so it went negative to positive, went through the undefined, and we're going to graph this in a little bit, and we'll see that we have a cusp. Okay, and then the last thing we have to write about is relative max, and that would have to go from positive to negative, and we know that doesn't occur. Again, does not have a relative max, never changes from negative to positive. All right, let's bust out the graph and calculator and plot this on the graph. Okay, so our original function is x plus 2 all to the 2/3. I always put these in parentheses. If you have the newer calculator, you don't really need to, but if you're doing a caret button, it should look like mine. Like I could get away with, because it does put it up as an exponent, I could get away with just writing it as 2/3. But if yours doesn't put it up there, then write it as in parentheses and then plus 1. And let's see what this graph does. Let me change my zoom standard. And there's my cusp. And I'm even going to now change my window so that my window is exactly like what the graph on the problem is. So it's going to go from -11 to 7. And that way, whenever I'm given this, there's no excuse. -11 to a 7, scaled by 1. My y's go from -7 to 11. And now I'll get a much clearer picture of how it looks. Um, compared perfect. So it looks like the cusp has a point where the minimum is going to be, again, we knew it was going to be when x equals -2. If I substitute that into the original, -2 plus 2 is 0, all to the 2/3 is going to be 0, 0 to the 2/3 is 0, plus 1 is 1. So it's going to be -2, 1, and that's this point right here. And then I can figure out these 2 points as well. And let's go back and let's graph this. So we just did it. -2, 1, and we can plot a couple more points. These 2 points are on there, and it looks like it crosses through. Again, just said sketch a graph, so we don't have to be that exact. And this is our original function, f of x. Okay, and so what we find out, and right on the bottom of this, and I don't have it on the video right now, but so the first derivative, f prime of x of a function, identifies intervals where a function's increasing, decreasing, has a relative max, or relative min. Similar fashion, the second derivative, f double prime of x, identifies interval where a function is concave up, concave down, or has a point of inflection. And since the second derivative is the first derivative of f prime of x, then the same relationships that exist between f and f prime of x must exist between f prime of x and f double prime of x. That's where it gets a little confusing as you're going back and forth, because we're going to be able to go back and forth from the original function to the second derivative, obviously the original function, the first derivative, and now from the first derivative to the second derivative. So we're going to have to keep all these straight. All right, so that's part 2 of day 33, 34 notes.